I introduced you to the various types of springs yesterday, and we'll focus on some of the ones we didn't talk to in detail yesterday. Here we see the extension spring, which gives you a pull force, and also the drawbar spring, which I mentioned briefly, that it looks kind of clumsy and cumbersome, but it has the advantage that it doesn't have any hooks, and when it breaks doesn't come totally apart because the coils will simply collapse and the two pullers will prevent it from separating totally, whereas when this thing breaks, and it usually breaks at the hook, it just goes flying. And I think I also mentioned that they're wound with a preload so that the coils are tightly together. The coils are, as with the compression spring, the coils are in pure torsion plus direct shear, but the hooks are in bending. So right where the hook gets pulled out of the last coil and becomes the hook itself, right there, you're going to have a combination of bending and torsion. So the stress state is worse there, and that's where they fail usually. I don't show a picture of this, but I've seen this used to good effect in machinery. Imagine that you don't have any hooks at all on this guy, you just chop it off. So I have what looks for all the world like a thread in the form of those coils wound tightly together. And now I turn in a lathe a plug that looks like a bolt, but has the pitch of those wire coils, and I screw it in to the coils as if it were a nut. And I have some detail on that, so I got something to pull on, and I can put one of those at either end, and now I can pull that spring open, and I'm distributing my load over several coils, and I don't have the stress concentrations. And those things last quite well. I've seen those used in machines that run 24/7 and last, better part of a year before they give up the ghost. Whereas one of these in a machine running 24/7 is not going to get through a month. Yes?
Unwinding a little bit.
You can run into that problem, but you have to clamp them in some fashion so they can't unwind. So if you have a grip, you're going to be grabbing both ends with something, right? One's fixed and one's moving. And so that's going to keep them from twisting. They typically go in 3 or 4 or 5 coils, so you've got a pretty good overlap inside there. Now here's some detail on the nomenclature. It's pretty much the same as for the compression spring, except that I've got these hooks on the end. And as I mentioned the other day, because of the preload, your force deflection curve looks like this. There's a threshold above which I have to go before it starts to actually move. So this F sub I represents the initial force in the spring coils themselves. And so the spring rate is then the difference between the force I'm applying and that initial Fi divided by Y. And that looks very similar to what we saw for the compression spring. Wire diameter to the 4th power, coil diameter to the 3rd power. NA is number of active coils. The spring index is defined the same way. It's big D over little d. And they give a preferred range for this torsional stress of the initial tension as a function of spring index, and they prefer to keep it in this band. And these expressions that you see here for T sub I represent the envelope of that band. So with those two equations, I can determine where my T sub I lies for a given combination of parameters. Deflection equation, from which the K is derived, looks like this. And it's actually the same equation as we had for the compression spring, except we have this difference of forces instead of just the applied force. This is exactly the same slide that I showed you yesterday for compression springs. We have a direct shear component. Up here we have a torsional shear. They add together. That offsets it. Then we have the same stress concentration on the inside of the coil from the curved beam problem. This is the same set of equations I showed you yesterday. We're going to do the same trick. We have TR over J plus F over A. This is my torsion. That's my direct shear. And they happen to be over different denominators. We want to make those the same. We bring in C as a factor, D over D, substitute that in, and we modify them such that I get them over the same denominator now, because this D cancels out one of those cube D's. And I now can combine those two terms. Then I can rearrange them in the fashion shown here and isolate this term C by bringing back in D over D. So I take the D over D out, put C in, do some manipulation algebraically, then put it back in, some further manipulation algebraically, until I get this expression in which I've converted it from the sum of two things, which we started with up here, to the product of two things. And the product, the term in the parentheses, is the direct shear factor, so-called. And so we can just give that a name and write the equation in a much more compact form, with this Ks being the shear factor, equal to 1 plus 1/2 over C. And Wall did the work on the extension as well as the compression springs way back, and came up with this Kw, so-called Wall factor, which includes both this and the stress concentration due to the curved beam, which is called K sub C. So Kw includes Kc and Ks, it's their product. So if I want to get the Kc, I can simply divide Kw by Ks. And that gives me the standard arrangement for shear stress, including, this is now including the direct shear, because that's now wrapped up in the Kw, and also includes the stress concentration, likewise in the Kw. And I can then find my shear stress condition. But that's not the end of the story. That was the end of the story, essentially, for the compression spring, but now I got to deal with these hooks. So I have to look at the geometry of the hook. It's a curved beam, and that theory is developed back in Chapter 3, and it's that derivation that generates this equation. So we have a sigma at point A, which is right here, which is on the inside surface of that curved beam. The force is pulling this way, and the coils are pulling back that way, and so we have a bending moment trying to open that up, so trying to spread that loop or hook out. And so we have a tensile stress on the inside surface and a compressive stress on the outside surface. And that sigma at A is some factor Kb, which is a stress concentration factor for bending that Wall also developed, which is equal to this concoction here, where C again is a similar idea to the spring index. It's given a subscript to differentiate it from the pure C. It's 2 times R1 over D, where R1 is simply the radius, the mean radius of the end hook, which is typically the same radius as the spring, because that hook is made out of the last turn of the spring, just folded out. And D is the wire diameter. So I can get the stress concentration factor thusly. This just comes out of the bending equations. So big D is again the coil diameter, F is the force being applied to the hook, and little d is the wire diameter. So pretty straightforward for that calculation. And we also have a torsional stress at point B, where we're just coming off the coil, and that's found from the same equation as before, but with a different factor, Kw sub 2, which is now going to take into account this radius R2, which is the bend radius where I take it out of the coils, which is typically quite a small radius. And that then bumps up the stress due to the torsion at point B. So it could fail either of these locations, so we typically just calculate both of those numbers and compare them to the strengths of the materials. We talked about spring surge yesterday, and it's the same deal with these extension springs, except that the formula's, I think, a little bit different. Let's see, well, if I had both ends fixed, it'd be the same, but that's not common. In other words, I'd have to be holding on to the two ends of my extension spring and not allowing them to turn at all, right? So if I just grab the two loops and pull, I don't have a moment joint at the ends. It's free to change slope. So that would be a different equation than I'm looking at here. But this equation that you're looking at is for the compression spring with both ends held, theoretically, so they can't do any wobbling, right? So that's a fixed kind of constraint. And that's much more difficult to do with an extension spring. Although I think with the screwed in ends, you stand a chance, because if I then prevent those screwed in ends with their associated detail that I'm grabbing onto from doing any wiggly this way, then I could postulate that I don't have any angular deflection at the ends. So this would be the same as a helical spring and compression if I could keep those two ends fixed. And if not, there's another equation for it. This is a similar table. The number's not exactly the same as you had in an earlier table for helical compression springs. I don't remember the exact details of what numbers are different, but there are some slight differences here. But again, we can get an estimate of bending yield strengths as opposed to torsional yield strengths, which the other table was for, as a function of percent of ultimate tensile strength. So here I have a bending and a torsional number for 3 possible materials that typically are used in this kind of spring. Similar table as we had before for the torsional fatigue strength, but now it's for bending fatigue strength. Stress ratio R equals 0 means this is a so-called repeated stress going from 0 to something back to 0 all day long, so I have an equal mean and an equal alternating component. Same slide we saw yesterday. Lots of data on springs of this type with repeated stress show these numbers for good estimates of the endurance strength uncorrected, thus the prime. W stands for wire here to differentiate it from the S sub E prime we used before back in chapter 6. 45,000 psi for unpeened and 67,500 for peened. And is not fully reversed. I showed you a similar study for the compression spring. This is a different picture. Looks similar, but the curves are different. So here I have safety factor for coils and torsion, and also hooks and bending as a function of spring index, which is sort of what you hang your hat on for spring design. At least I do. Different people design them differently, but as I mentioned yesterday, I usually start by picking a big C and then plunge in with some other assumptions for wire diameter or whatever and see what comes out. Usually I have a good idea of what I want for D, big D, because I'm trying to fit it in someplace or put it around a post of some sort. And you have a similar situation in your case. The packaging is going to dictate my big D, but the little d can be anything. So I'll let that come out in the wash and see what happens. Quite often I solve this problem for put in the safety factor I want and let it back out the D, the little d. That's a very quick way to do it. So it tells me what size wire I need to get that safety factor for this coil diameter and this C D over D ratio and so forth. So this tells me how my various parameters free length will vary. So I can see there's an optimum or a minimum value on the free length curve that says if I want the shortest possible spring, I want around a 7.5 value of C, if that's my goal. And if I go to rather low values of C, my free length is going to go up rather drastically, less so if I go over this way. So these show me trends. Outside diameter just goes up linearly with CO, which makes some sense because C is big D over little d, and this is for constant wire diameter. Weight of spring comes down slowly as I make it bigger. And the other, I've already discussed the safety factors. With a model of the sort we were discussing this afternoon for the spring equations, you just generate these curves. And looking at those trends gives you some clue as to how to go about designing the spring that is best suited for your situation. Different type of spring altogether, a so-called torsion spring, named because it gives me a twisting torque as opposed to a force. But ironically, just as the compression or extension spring gives me a force, it nevertheless has torsional stress in it, as if it were loaded with a torque. And this is the reverse. So this has bending stress when it's loaded with a torque. Because what happens is when I I hold one ear of the spring. This is just a coil. You can see some pictures of them here. You saw them being made in that video yesterday. And you just take the last one off tangentially and make it whatever shape and length you want. And these are going to grab around something in your assembly. You pretty much always have to stick this on a pin to keep it from flying off. So you stick a loose-fitting pin inside of it, leaving it plenty of clearance, because as you compress this, the coil gets smaller, and you don't want to pinch the pin. And there's some guidelines that will come up on a later slide about what percentage of clearance you should leave. We can calculate the minimum diameter of the coil based on the amount of theta we put into it, and then we want to leave some wiggle room by making the pin a bit smaller than that. So what we have here is a curved beam in bending. So we can get tensile on one side and compression on the other. Now in this case, and which way is it going to go? Looks like I'm going to have tension on the outside, doesn't it? If you think of pulling this up this way, the outside surface should be in tension, and the inside surface should be in compression. Now the inside surface is the one that has the worst stress concentration factor. So it's helping us that the tensile stresses are on the outside, where we don't have such bad stress concentration, because the tensile are what are going to kill us in fatigue, not the compressive. So unlike the helical type spring, the compression or extension, where we focus on the inside surface to calculate our stresses, here we're going to look at the outside surface, because that's where the tensile is.
So,
well, here you're talking about the compression springs or these guys?
I guess either. On springs in general, it's for all springs the maximum.
They're most likely going to fail where there's high tension.
Okay, they're going to fail in tension. Okay.
Yeah. In fatigue.
Right.
Now, in yielding, I can crush it. You know, I can bend it in compression as well as tension, because it's roughly equal strength in both directions, almost exactly for steel. It's an even material. It's just as strong in compression as in tension. Unlike the cast iron is huge compressive strength and lousy tensile strength, about a factor of 3, right? But ductile steel, like this wire, is the same strength in both directions. So if I'm simply trying to break it statically, I can compress it till it yields, or I can tense it till it yields at about the same level. But in fatigue, it's a whole different can of worms. Now, in fatigue, compression is my friend. Compressive stress is my friend. And tensile stress is my enemy. That's what causes the cracks to grow and open up. Okay? So since we're generally dealing with the fatigue situation here, you know, one of these springs in static loading is very uninteresting. You know, I put it in there once. If I don't yield it, I'm done. I go away. I'll leave it. Forget about it. It should never break, right? But when I start to do this with them, that's when things get interesting. And then I'm going to fail it in tension. And the tension in this happens to be on the outside surface. So here's an equation that lets me calculate the active coils. It says they're equal to the number of body turns, that'll be the number of total coils, number of times you went around, plus some contribution from the ends, because those can also bend. You know, these are in bending, so this is a cantilever beam that's adding some deflection. If I'm measuring deflection out here at the end, or part way to the end, then my total angle is a combination of how much the coil wraps up and how much this ear bends, and this ear also. So we're going to take that into account by adding a little bit for the ends, and the simplest case is that they're straight, which they may or may not be. And in that case, we can more or less fold the effect of the two ends bending into effective coils, as if we added some coils to the thing and didn't have the ends. That make sense? So we're saying take the length of each of the tails. L1 is one tail, L2 is the other tail. Add them up, divide them by 3 pi times the coil diameter, and that gives me an effective additional coil, if you will, that has more or less the same deflection as the end pieces would for those lengths. So we're just putting it in different terms, so we can then throw it in the pot, add it to the actual number of coils, and call this our NA, our active coil, so-called. That make sense? You all follow what I did there? So here are the expressions for deflection and spring rate. And now the deflection is expressed in either radians or degrees or revolutions at your choice. The revolutions are often used, would be fractions of revolutions in some cases. Many of you, I'm sure, at your parents' home have a overhead garage door that opens with the push of a button, or even if it doesn't open with the push of the button. It's got a torsion spring, usually, that is counteracting the weight of the door. So you don't have to have a 42 horsepower motor to lift that heavy door. Those doors weigh a lot. So if you counterbalance the weight of the door, you just have to overcome the friction and accelerate it slowly to get it open. And you have like a, a third horse motor or a half horse motor or something on it. And that spring, I've got 16-foot doors, and that spring is 16 feet long. Yeah. Coils wrapped around a torsion bar, essentially, and they are pulling on the cables that lift the door's weight. And those I had to wind up when I installed the doors. And they give you a bar of steel the size of your finger and about that long, so it's just a lever, and they've got holes in this collar, which is in the end of the spring. And there are some set screws. So you stick the thing in, and you got two of them. You rotate it up, you stick another one in so it can't come back, that's against the door, and you tighten the set screw, and then you take them both out and do it over again. You keep tightening, untightening the set screw. You do that for about an hour. And you wind, seemed like 100 turns into this thing before it had enough torque available, enough force to lift that big door. So this could be some number of revolutions in a particular case in a spring like that, or it might be some fraction of a revolution, a few degrees. Depends on the application. So M is the applied moment, which would be the force applied at the leg times the length of wire. That's the total length of the wire in the spring. So that's the length of the piece of wire that you made the coil out of. Because that's effectively your whole beam is that long, right? E is the Young's modulus instead of the G now. I instead of J, because we're in bending. And these are just conversions to radians and so forth. And if we have round wire, we can stick the geometry in for I and so forth and reduce it down to an expression that you see here. Now, you don't have to have round wire. In fact, it's not uncommon to use square wire or rectangular wire in both of these types of springs. And the advantage of the rectangular or the square cross-section is, for a given volume, they have a bigger eye, right? If I take a square that's 2 millimeters on side and a circle that's inscribed in the 2 millimeters, I have more material in the square. I got the corners. And so my I is larger, and my J is larger, too. So if I'm trying to pack the most energy into the smallest package, I often go to a rectangular wire. Now, it's not as commonly available. I introduce stress concentrations. There's a whole bunch of negatives associated with it. So it's not that often used. I've seen it used where, in a camera application that I remember from years ago, we needed an energy storage within this tiny shutter, and we just didn't have any room for anything, and we went to square wire to get the maximum energy into the smallest space possible. So this all reduces down to an approximate expression, which turns out, when you evaluate these constants, to be around 10.2. Moment, coil diameter, number of active coils, wire diameter of the fourth power, Young's modulus. And then it says here the fact that 10.2 is usually increased to 10.8 to account for the friction between the coils based on experience, and that makes it 10.8. So that's the typical design equation for the deflection of a torsion spring. And it's approximate, obviously, because we have only one decimal place and there's a squiggle over the equal, because we have some windage in there to take care of the friction, which is quite variable. And you can always get the spring rate from this expression by just rearranging it. The spring rate is going to be torque over, or moment over, angular deflection units. So Newton meters per degree, or whatever, however you want to express it. Inch pounds per radian, or rev, or whatever unit suits your purpose. I mentioned earlier that as you wind the spring up, it gets smaller in diameter. and that's referred to as coil closure. So we can calculate, oh, and it's important to note, as I say here, that it's usually and should always be loaded to close the coils. You never want to try to open the coils up because the residual stresses are in the wrong direction and you're liable to fail it. So if I close the coils, I've got residual stresses helping me rather than hurting me. So it's considered bad form in engineering to try to open up the coils, which is another way of saying I should never fully reverse load this thing, right? Just like we don't want to do that for the other springs either. We want to go always same direction, either 0 to something or something to something. So the minimum diameter, di min, is the mean diameter times the number, NB was the number of coils, I think. I had it back here someplace. Yeah, right here. Number of body turns, that's what the B is for, I'd forgotten that. Number of body turns, so that's the actual body of the spring. Over NB plus the deflection in revolutions minus the wire diameter. And then it says if you're going to put a pin in this thing, you should limit it to about 90% of that number. So you have 10% of clearance in there. So you never want to get it tight on the pin, because then you're going to overstress it and break it. The maximum coil body length at full windup is this expression, L max, wire diameter, number of body coils, plus 1 plus theta. Now what's happening here, take this guy from here to there. I just added a little bit of coil. Maximum coil body length at full windup. The stress concentration in all of these things. And the outer fiber is MC over I, but it's a curved beam. So as shown back in, it was chapter 4, not chapter 3, I misremembered. Stress is concentrated at the inside of a curved beam. So we derive the concentration factor for the inside of a coil round wire as this, and at the outside it's this, and C again is just the spring index, D over D. And so I get a slightly different number here because there's a difference in sign. The only difference is this is a minus and that's a plus. So if that's bigger, this is smaller. So there's slightly less concentration on the outside than the inside. Compressive bending stress at the inside, loaded to closest coils, is this expression, where this is the KBI, which is the inside edge stress concentration. And at the outside coil diameter, it's this expression right here. And so here we have the minimum, the mean, the max, and the alternating. All the stuff we need to do a fatigue type calculation. You're going to be repeated stress, so you're going to have both a mean and an alternating component right here, which we get from these two. One is the sum divided by 2, the other is the difference divided by 2. And here's what I was saying earlier, that for static yielding of a torsion spring, the highest stress is inside the coil, but for fatigue, which is tensile stress related, the slightly lower maximum tensile at the outside is the concern. So for strictly yielding, I want to make sure I don't yield the inside of the coil, so I would look at the inside surface. But for fatigue, I'm going to look at the outside. If the spring is loaded to open the coils, which is not recommended, it must be stress relieved to eliminate the residual stresses from coiling, and then the inside coil stress should be used to calculate the components for the fatigue failure calculation. So what's that saying? Well, first of all, what is meant by stress relieved? It's essentially annealing the part. So I take this piece of wire, which has stresses up the wazoo in it from getting drawn through those dies to reduce the diameter. So it's got a whole lot of built-in stress already. And now I take and I wrap it around a rod real tight and yield it in the process. And of course it springs back a little bit because the elastic energy comes back. The yielding is permanently there. And now it's got some more stresses in it. So it's saying if I for whatever reason, want to load this opening the coils, I better get rid of those residual stresses. And the way to do that is I put it in an oven and I bring it up to a magic temperature, which is pretty hot, and then I let it cool slowly. And so I let those molecules all rearrange themselves in there and get rid of all those residual stresses. That's called stress relieving. This is often done after making a welded part, because the welding process puts all kinds of crazy residual stresses in, because you're locally heating with your electric torch some strip where you're bringing in molten material to make the weld, and then you let it cool, and it shrinks and it gets distorted, and you leave a whole bunch of stresses hanging around in there. So if that's going to be subjected to any serious loading in service, you probably want to cook it in the oven and get it back to more or less as-made steel conditions. Okay? That's what they're talking about here. But then the same breath they're saying it's not recommended that you load them that way. Material strengths, we already discussed the fact that these magic numbers that come out of a lot of testing are still valid. But those are torsion, and now we have bending stresses, and we can use distortion energy theory to go backwards from torsion to tensile, just as we used it originally to go from tensile to torsion, right? So I can take these numbers and I can create a, I'm going to call it SEW sub B for bending, so that's going to be a tensile parameter, and take this magic number SEW prime and divide it by 0.577, which is the distortion energy ratio, right? So we'll put it back into the tensile regime by dividing that 577 out, and we get these two numbers, 78 and 117,000 psi respectively for unpeen and peen. And now I can use this parameter, which is just as good for my calculations against failure and fatigue. So the yielding failure is simple. It's simply the yield strength divided by my inside maximum stress, inside coil. And now if I'm loading this the way I'm supposed to, which is to close the coil, then on my sigma outside, the O is for outside, the I is for inside here, is going to be my parameter of interest. And this is just, this messy looking equation comes about as a result of solving for the intersection of two lines of which I know the expressions for. One line is the Goodman line, coming down from S sub E, from your direction, be this S sub E over here, and down to S sub UT over here on the horizontal axis, right? And then we have a load case, which is my sigma initial, if there is any. There may not be any here because, well, no, there would be, because I put some preload into this thing. So there's some initial stress. So I come over from 0 on the axis, and I start there, and I go up at an angle of 45 degrees, don't I? Because I got equal, if for a repeated load, I've got equal mean and equal alternating components, and I go up that amount, and that's my load case. So if I calculate that line, take that expression for that line and the Goodman line and find their intersection, that's where they break. And that's how this expression that looks so messy was derived. And the derivation's in the book. I just didn't put it in the slide. And it was derived back in Chapter 6 as well. Same expression with different labels here because we're talking about things that are on the outside and so on. So S sub B is the same as it was in Chapter 6, but we've generated from this very extensive torsional data, so it's a good number, all fully corrected. SUT is just what it is, ultimate tensile of the material, and I have my mean and my min in this case, and my min up here, and my alt. Now the mean minus the min is in there because I've got this F initial and F mean, right? So this is my initial stress before I ever start to do this to it. So I'm not going from 0, I'm going from some other value, sigma min, up to sigma mean, if that makes any sense. Any questions about these torsion springs before I switch topics totally? Okay, Belleville washers. These are cool. These are one of the neatest springs I've ever met, and you'll see why in a minute. They look very simplistic. They're just a washer that's been squished So it's got a conical shape to it. I think of it like a Chinese hat. So it has a height h, an outside diameter do, a thickness of metal t. It's just a flat piece of steel when it starts out life, and some inside diameter di. So just 4 parameters will define how it behaves. And these are typically made in steel because you need the strength, and they're typically hardened so they don't yield readily. And they give me really high forces, because you can imagine if I'm going to flatten that out, I've got to do some serious distortion to that thing. You know, the cone is a very strong structure, as is the cylinder. It takes a lot of force to crush that. So this is a very resistant to being flattened, and I can take it all the way to flat and beyond, as you'll see. So there's the same picture. And the interesting thing about this is the load deflection characteristic is not linear, and I can't just express it as a K. It has many Ks, depends on a whole bunch of circumstances. So I have to calculate the load deflection behavior from this complicated expression. Now let's look at what's in here. This is the force that I'm applying to it. E is Young's modulus. Y is my deflection in the vertical direction. I didn't show it in the picture, but Y is up and down over here. K1 is some factor that's defined here. We'll come to that in a minute. Big D O is the outside diameter. That's Poisson's ratio there. H is the height that this starts out life as, what I made it to. T is the thickness of the stock. Y again is the displacement. So that's all I've got in there is some geometry and some material properties in the form of E and Poisson's V. The K1 is a stress concentration factor of sorts, where we have it equal to 6 over pi times the natural log of RD. Now RD is much like the C factor for the other kinds of springs. It's a ratio of 2 diameters, but in this case it's dO over DI instead of big D over little d. So RD is the ratio of the diameters. That's what the letters stand for, ratio of diameters. So that's appearing in here to various powers, and it also has the log taken of it. So this is a messy function. And I can calculate the load at the flat position, which is when y is equal to h, when I've smushed it down to through the distance h. And so the force at the flat is this same expression with h substituted for y, essentially. So far, so good? So I got this horrible looking expression, but with my computer, they don't frighten me anymore. With my slide rule, I would have been crying when faced with that, especially because of that natural log. Because you really can't do a natural log on a slide rule. It's log base 10. So this was an, oh my God, how do I do this moment in the bad old days. But now, who cares? I got a log thing in my computer. Do it, piece of cake, right? No problem at all. So if I take that equation, or that set of equations, this one right here, and I crunch it, and I normalize things so that this is percent deflection instead of any particular number. So it represents any case. So the way I've done this is 0 is as it came out of the box. So that's the picture over here. I'm at 0 deflection. When I get to 100%, that's flat. So that's 100% of flat. And I go through the other side, and I go to the inverse picture of this. So now the hat is downward, and I'm at 200% of flat deflection. I'll show you in a minute how we physically can do that. This will go all the way through, pop over the other side, and then come back. Now, this axis here is percent force to flat. So 100% on this axis is whatever force I need to make that flat. We had an expression for that a page ago, which said F flat was equal to some mess. Okay? So I'm calling that 100%. So I need 200% of that to get all the way to the other side. Okay? So this is simply a force deflection plot. This is my spring rate, normalized so I don't have to bother about dimensions and units and all that stuff. The different members of the family are represented by a ratio which is h over t. Well, h is just the height of the hat, and t is the thickness of the material. And I have total control over both of those because I'm going to make the thing, right? So look what happens. When h over t is the magic number of 0.4, it looks just like a regular linear spring. and I have I have a real K, a constant spring rate. But if I make h over t a little bit bigger, like 1, it starts to give me kind of a funny shape, almost like two parabolas. I get to h over 2 equal to square root of 2, and that shape becomes, as you see it here, and it's really flat in the middle, which means if I operate around that 100% point in deflection, I have a 0 rate spring, constant force. There's a lot of applications where you would like constant force over some deflection. One of them is a clutch. Clutch springs are sometimes made with these because over the small distance of engagement and disengagement of the clutch, which is probably a millimeter's worth, if that, I can get a constant force on that clutch plate. Very handy from an engineering standpoint. Now I keep going and I crank this up to 2.275, and now I get a double hump. And notice, and I can go further to 2.8, and it's a more serious hump, and I'm going all the way from 0 to 200 and back again through flat and to the inverted condition, and it's bistable. Because when it gets there, it's no way to get back. So I now have a switch, which if I flip it that way, if I push it past center, it's going to flip all the way to that maximum deflection, and I have a little switch contact waiting there for it. And bing, the light's on. Now I push it the other way, and now a different light's on, or the light's off, or whichever you like. Back and forth all day long. Bistable device. So there's all sorts of funny things you can do with this simple little thing, which is nothing but a washer that's been knocked into a cone. Very clever. Mr. Belleville was a Frenchman, 1897 or something like that. So here's the way you make it go over center. You've got to go to some trouble to mount this thing. So you make up an arrangement like you see here, where I have a plunger that has a little step in it, and I put a snap ring here so I can capture the inside diameter of that guy. And then there's a thread here, and I have a little relief, and this plug screws into it and stops just at the right place so that I capture the outside diameter. So typically the ground plane would be this outside thing, and I would put a force one way or the other on this, and I can pop it above center or pop it below center. If the ratios are such as to give me the two humps, it'll stay. If it's a 1.414, this will simply go back and forth. I let it go, it'll come back, right? Because the slope's always the same, or 0. This is a slightly blown up version of that 1.414, and I've drawn this with a little shaded window around a piece of the curve to show you that this, remember, this is percentage, and this I'm only going to plus or minus 10% around the flat. That's what I blew up. I'm looking right around the flat. The other was 100%, plus and minus. So this is 1% of the total deflection to flat, whatever that is. And I'm showing you that over plus or minus 10% of the deflection to flat, I'm getting plus or minus 1%. Actually, I'm getting almost no change in the deviation from force. If I go out to 80 to 120, I'm no more than 1% different. So I've got a force that's constant within 1% over 40% of the total deflection available from this thing. I can do some clever design things with a device like this, and they're dirt cheap because they're just a piece of stamped metal made in great quantity. Has some horrible stresses in it, as you might imagine. Here's the ugly equations for them. The worst case stresses are at these 3 points, right at the corners. So C means compression, T means tension, I is inside, O is outside. So I got formulas for each of those. And the K's are even worse. So all these K constants in there have these logarithms in them and whatnot. So these are messy expressions. But again, my computer doesn't care. I can do those fine. So now, disadvantage of the Belleville is I get very little stroke. You know, you're talking about a millimeter or thereabouts before I overstress it. So if I need a lot of stroke, it doesn't fill the bill unless I stack them. So if I put a whole bunch of them together in series, as I show in one of these pictures, one in the middle, I get the sum of all those deflections, right? If I put them in a parallel stack like this, I get the sum of all their forces. So I get a really big force out of that guy. A lot of friction, because they're rubbing on one another as they move. So I wouldn't expect that to respond very rapidly to some dynamically changing thing. But where these are used a lot is as die springs. You know what a die spring is? You know what a die is? A die stamps metal. So it's hardened steel. They often are this big or bigger, depending on how big they stamp car bodies. Those, my arms aren't long enough to demonstrate. Okay? So the fenders of your car, the roof, are stamped in these dies. They're contoured to the shape of the part that you're trying to stamp. You bring in a flat piece of steel or any other metal, and you push a button, and down comes the top half of the die called the punch. Wham! It's a hammer. It's a shaped hammer, and the shape exactly matches that of the die, and it just smushes it into position. That's how you make pots and pans. That's how you make little latches. Make all sorts of metal parts that have funny shapes. The latches for your car door and that sort of thing are typically stamped. So, where was I going with this? I have to have, this is a huge press. I bring that down, I stamp the part. Now I pick it up, and things are stuck on the punch. And the part stays with the punch. And I want to get it off. I punched a bunch of holes, and I want to get it off the punches that are in the holes. So there's what's called a stripper plate. It's a third piece. It rides with the punch. It's almost as big as the die, and it has these Belleville springs behind it. And it's sticking out by the amount of the springs as it comes down. It hits first, the springs compress, the punches do their thing, it comes up, and the springs go poof, push the stripper plate out and knock the part off. Okay? It's a stripper. It's stripping the part off the punches. And so you've got very little space to deal with. These are ideal for that. You put just enough you make a pattern of them, like a matrix, pushing on this big plate with these Belleville springs. Very common application for them. They have lots of use. So, back to the examples. I'm not going to go through them in class. They're pretty straightforward. I think they're quite clearly explained, if I do say so myself. You can follow them. If you have questions, come see me, and it'll show you how to calculate these guys. It's really no big deal. The expressions look messy, but as I said, your computer can deal with that, right?